Okay, so very good morning to all of you. In today's session, we will be starting ISRO 2018 paper. So in this session, we will try to cover strength of material and machine design of 2018 ISRO mechanical engineering paper. Right here, when you see the question number 35, right? In this one, this question is basically from machine design. Already, as a very similar question they have asked in 2016 also. One more time they have repeated, right? This similar questions. Even before 2015 also they have repeated one more time this same ball bearing questions, right? Now in this ball bearing question, what is the main fundamental thing? Here we have to use load life equations, right? Here what we have to use? We have to use load life equations. Note down. Generally load life equation. Load life equation of a ball bearing of ball bearing. What is the load life equation we have for the ball bearings? So the load life equation, we know that I told you L, that is life is equal to what? C divided by PE to the power 3. 3 for the ball bearings, right? Whereas we have seen that C is nothing but the dynamic load capacity, and for a particular bearing that will be constant, that will be same, right? Here, so we can, if C will be same, so we can write L into L1 into P1Q PE1Q, that is equal to L2 into P2Q. Because C1, whatever the C value is there, C value will be same, right? C value will be same. So L, here we are writing L into PEQ is equal to CQ. This CQ will be same for a particular one bearing. Until unless you are changing the bearing, C cannot change. That is the dynamic load capacity, right? What is C? Dynamic load capacity. So the life of the bearing is given as 24,000 hours at a load of 10 kilonewton. If the load is increased, if the load is increased to 20, that means if it is 20 cube, then what is the life of the bearings they are asking? So it will be 8. So that is going to be 3000 hours. 3000 hours. B will be correct. So remember, either we can write the life of the bearing in million revolutions, in billions of revolution, or we can also write in terms of number of hours, right? If you want to convert into million of revolutions, then you have to write life in hours, the number of revolution, right? That is life in hours, RPM. Then how many revolution it is taking per second, right? And total number of seconds which are available. That will give me in terms of millions of revolutions, in terms of total number of revolutions. If you want to get, if you want to convert into from hours to the number of millions of revolutions, right? In that case, you can convert. And remember one more thing, one more important thing. Whatever the L is there, what is L? L is L10 life of the bearings, L10 or L90. That means we will try to note down the values of life of the bearings when the test has been conducted for n number of bearings, and we'll see when the 90% of the bearings are going to fail, or we will note down the values of 10% of the bearings which are going to be the moment 10th bearing will be failing, then we will note down the life of the bearings, right? How many number of revolution it has gone before the failures, right? So note down. We don't define L50 life. We do not define L50 life. From this equation, whatever the L we will be getting, that is L10. So make a note of it. So here you can note down one more important thing, L10 or L90, right? Regarding this, just note down. The nominal life of a group of identical bearings is defined as the number of revolutions that the 90% of the bearings can survive. Note down. L10, we say L90. L10 here, the meaning of 10 means probability of failure. Probability of probability of failure. As I told you, only doing the previous year question will not help you. You have to solve all other questions regarding that the question which they have asked, right? L90 will be the probability of survival. Probability of survival. This we are calling nominal or rated life. Nominal or a rated life of the bearings. What is the definition? Not on each and every things are important. Next question would be what? They might be asking you not the life of the bearing. Whatever the life they have asked, that is a nominal life. That is a rated life indirectly. Nominal life they have asked. Who knows? The next time they will be asking you average life. But how you will calculate? How you will calculate? So please note down. Definition will be the nominal life of a group of identical bearings. The nominal life of a group of identical bearings is defined as the number of revolutions, the number of revolutions that 90% of the group of the bearings, 90% of the group of the bearings can survive, right? Before evidence of first fatigue failure. It is denoted by, it is denoted by L90 or L10, right? So for example, to have if you want to explain to layman, then how can you explain? For example, we have 100 bearings. 100 bearings we have taken. And L and T, that means 90% of the bearings will be surviving, let's say 100 million revolutions. Before evidence of the first fatigue failure, let's say they have made 100 billion revolutions, 1 billion 10 lakhs, 100 into 10 lakhs revolution they have made, right? That means 90 bearings will make more than or equal to 100 billion revolutions, and 10 bearings which automatically consider as failure, they will not be making uh, million revolution. They will be making less than 100 million revolutions. What we have said that the number of 90% of the group of the bearings can survive, right? Let's say we have defined the nominal life or rated life 100 million revolutions. Then 90% of the group of the bearings. How many bearings are there? 100. 90% means what? 90 bearings. 90 bearing will be what? Undergoing 100 million revolution. At least 100 million revolution before undergoing or before evidence of the first fatigue failure, right? The moment, my dear friend, 91st bearing, the moment we have the 91st bearing, we will be failing. The moment 90th, 91st bearing will be failed, or let's say the moment we are trying to rotating one not 1 million revolutions, or even a single revolution we are doing, then there may be chances that the fatigue failure may occur in 91st bearing. That will be considered as failure, right? So please make a note of it. Then, sir, what is the average life? What is the average life? Average life we define L50. That means 50% of the group of the bearings. And automatically, my dear friend, it's a very common sense. Average life will be automatically larger, will be more as compared to the 90% bearing. Because we are waiting till 91st bearing will be failing. Getting my point? So obviously, the chances that the life will be lesser as compared to this life. So this will be L10 or L90 we can write. As the number of revolution will be keep on increasing, the number of revolutions, as the number of revolutions keep on increasing, the chances of failure or probability of failure will also increase. You are conducting, let's say, 100 bearings, and you have started your experiment. You start rotating your shaft, bearing will also be start rotating. Then you have continuously doing this setup or experimental thing. Then you are waiting for the 91st bearing failure, means you have rotated too much, then chances of failure will also be very very high. But you are waiting for L50 means 50% bearings gonna fail. That means you are waiting for 50th bearing. When the 50th bearing is failing, then you are noting down the number of revolution. Automatically that will be higher as compared to the L90 life of the bearings. That's why we have L50 life is 5 times L90. So in the same problem, if they would have been asked what is the average life in hours, same question, everything is same, but instead of nominal life, they would have asked average life, then what would be the answer? 15,000, right? This type of thing they will do nowadays because of competition, right? They will not simply throw a very simple, straightforward question. Now here, note on the next question. The main objective of short pinning. Again, same question. So this question they have asked at least 3 times in ISRO. Short pinning, I told you we are doing for increasing the fitting strength of our material. How and why? You please go and watch previous lectures, right, of ISRO session. We have done this same thing, right? I explained you short pinning. We are introducing compressive stress, or we are basically with the help of this we are introducing compressive load on a material. Right. Compressive load basically not a harmful load. Compressive load is not a harmful load. Because of the compressive load, compressive stress will be developed. And I told you, as you keep on increasing the beam compressive stress, there will not be any significant reducing. There will not be any significant reduction in the fatigue strength or endurance strength of a material. Whereas, as you keep on applying mean tensile strength, your endurance strength will be keep on decreasing. This graph, let's say you have talked about the Gerber, we have here endurance variable, here we have this endurance strength, here we have ultimate strength, axis is what, mean strength, a mean particular load, mean stress. As you keep on increasing the mean tensile stress in the first quadrant, endurance strength will be keep on decreasing. Whereas when you apply negative mean compressive stress like this, the graph is showing like this, endurance strength is not at all decreasing, it will remain constant, right? No, no. This is also one of the important aspect of strength of material. The material that exhibit same elastic property in all the directions at a particular point, what we call. Again, it's a very simple. What will be the answer? See, we have different types of material: homogeneous material, isotropic material, isotropic material. What is the isotropic material? Note down. Isotropic material means it is a definition of isotropic material. Elastic properties are same in all the directions at a given point. Let's say you have this material, any material you have selected, and on this selected material, I have selected 2 points, P, Q, and R. 3 points I have selected. When elastic properties are same in all the directions at a particular point, that means at point B, elastic property, let's say E1, E1, E1. Let's say at point Q, we have elastic property E2, E2, E2. Elastic property may vary point to point, but in a particular any directions, you take any direction at the same point, elastic property will not change. That is the isotropic material. There is a one more material called homogeneous material. What is the meaning of homogeneous material? Note down that also. Answer is C. We got the answer, but note down other things also. Elastic properties are same in all the points. Elastic properties is same at all the points. Elastic properties are same at all the points in a given directions. Let's say you have material. Again, select P, Q, and R. Now, my different. What I'm saying is that here you take any direction E1, right? You have selected any given direction. Let's say given direction is Y. In the y direction, my property, elastic property, will be E1, E1, E1 at all the points. And in x direction, let's say E2, it will be same E2, E2, E2 in all the directions. Let's say E3 in z direction, it will be E3 in all it at all the points. So homogeneous material is non-isotropic material. You can see very clearly it's a non-isotropic material. Why non-isotropic material? Because of definition of the isotropic material, material properties would be same at a particular point in all the directions. But at all the directions, whether properties are same? No. In a given direction, right? It has to be same. That is the homogeneous. In strength of material, whenever we select the material, we select the combination of these two. We select the material combination of these two. That means a material should be homogeneous, material should be isotropic material, right? As it is given orthotropic material also. So let me explain you what is the meaning of orthotropic material. No, no. Orthotropic material. It will exhibit. It will exhibit different elastic property, different elastic property in perpendicular directions. In perpendicular direction. That means, let's say E1 here, here it will be E2, here it will be E3, like that. In a perpendicular, not in a very any random directions. Whatever the direction you assume, that three direction must be perpendicular. Four direction they must be perpendicular. In all the directions, elastic property will be different. That is the orthotropic material. What is the example? Note on the example: wood, graphite, plywood, etc. Whereas homogeneous and isotropic material examples are copper, steel, you know, aluminum, all other examples of material which we use in our day-to-day life or in our industry. Basically in industries, whatever the material they follow, they we assume that it is a homogeneous and isotropic materials. No doubt. Heterogeneous means made up of two different kinds of material. That's a very different scenario. We will not talk about that. Okay. Here, note down a few more things regarding this impact strength. Impact strength. See, whenever we are determining any impact strength of a component, then which are all the tests we basically perform? Impact testing machine. Impact testing machine. What is the meaning of impact test? Generally, any object is there. Let's say you have setup, you have workpiece, you have table. There is a hammer which is being thrown at a height of h1, and it will hit this material. Again, it will be gone to the height of h2. So in this impact testing machine, we are hitting the material and we are testing whether it is able to, how much of energy will be able to absorb, and how the fracture is happening. So impact strength of a material is an index of toughness. How tough the material will be. Because I told you before failure, how much of total energy absorbed. That is the toughness. Generally, we measure this toughness for a brittle material. Right? Here we talk about the brittle material. Then for a brittle material, fracture toughness of a brittle material can be measured by IJOD or Charpy test, right? So down fracture toughness of a brittle material. Put a note. Fracture toughness of a brittle material can be measured by IJOD or Charpy test. And for ductile material, by tensile test machine, universal testing machine. Make a note of it. Why it is the IJOD and Charpy test? That is a different thing. We will see on some other day regarding these two particular tests. Note down the next question of strength of material. A composite bar, the bars in series. The bar consists of aluminum and steel is fixed rigidly at support P and Q as shown in the figure. When the temperature of the bar is increased by 10 degrees centigrade, the reaction at the supports will be what? The reactions at the supports will be what? Now here this is a bars in series combination. So first of all, note on the diagram, then we will discuss. The bars in series combinations subjected to thermal stress. So here there is no mechanical loading, thermal loading has been applied. Whenever you take two material, so once it is, I think all of you have noted down. Now let me explain you. So we have a bar, we have aluminum, we have steel, we have aluminum, we have steel. Then it is having a length of 2 meter, length of 1 meter, oh, sorry, 3 meter. Area will be what? 400. Area will be what? 200. That is the secondary thing. First, understand the concept. Understanding the concept is very, very important rather than data. Here, aluminum and steel, these two materials are connected in series, bars in series combinations. Whenever we have the bars in series combination, there will be certain reaction force. There will be certain reaction force. Let's say the reaction force is R. Of course, I can write R1 and R2. But here, summation of forces in x direction when you do, you will getting R1 equal to R2. There is no any other external force in between the bar or at the ends of the bars. We don't have any load. Only the load is a reaction force, and that will be equal. Now they are fixed at both the ends by the rigid support. These are the rigid support. Rigid supports are not a very flexible support. Even they will not permit even a single axial deformations. So what about the net deformation in x direction for both the bars? Has to be zero. Now in this one, it will consist of deformation in the first bar, deformation in the second bar. But what about deformation in the first bar? What about the deformation? Or rather, to understand like this, let me explain you principle of superpositions. What is the meaning of principle of superposition? Understand. You try to, what you do, you try to just increase the temperature and let them expand. What will happen? When you try to increase the temperature, what will happen? This particular bar will be extended like this. This steel will also be expanded like this. Initially they were like this. Initially they were like this. But now when we increase the temperature, when the temperature got increased, what will be happening? You first remove the right rigid support. You remove the right rigid support. Once you remove, when we remove right rigid support, once we remove the right rigid support, what will happen? They will expand freely. As there is no restrictions, they will expand like anything based on the property of the material or coefficient of thermal expansions value. What is that value? What is that deformations? This is the thermal deformation 1. This will be the thermal deformations 2. Sorry, this will be the thermal deformation 2. This will be the thermal deformation 2. What is the value? Everyone know that, right? Alpha 1 into delta t into L1 plus alpha 2 into delta 2 into L2. This is a total thermal deformation that could happen when the right rigid support would have been removed. But we know that in reality, there is a rigid support. There is a certain rigid support, and that rigid support will say you go back, you just go back. And how much of resistant, what is the resistant force, how much of resistance it will apply? It will apply total, whatever the deformation that would occur, the total deformation will be restricted. And how much of deformation, mechanical deformation, that could have been occurred in both the aluminum and steel because of the reaction force, we know that. What is that? Mechanical deformation, we know that PL divided by A. But here, what is the load in both the members? See that here and here, the load is what? Minus R. So minus R into L1 divided by A1 E1 minus R into L2 divided by what? A2 E2. That has to be zero. Nothing is permitted, right? So now when you combine and when you simplify, you can get the values of what? R. Alpha 1 delta T into L1, alpha 2 delta 2 into L2, R into what? L1 divided by A1 E1 plus L2 divided by A2 E2. You simply put those values, you can get R in particular Newton. That is a compressive. Put that values. Alpha 1. What is the alpha 1? 1 I am putting for aluminum. 1 I am putting for aluminum. 2 I am putting for steel. Alpha 1. What is the alpha 1? 11 into 10 power minus 6. Delta T1, 10 degrees centigrade. L1 is what? Everything you convert in mm plus alpha 2. Alpha 2 is what? 12 into 10 power minus 6 into 10 into 3000. That is equal to R. L1 divided by A1 E1. L1 is what? 2000. A1 is what? 400. E1 is what? 70 gigapascal into 1000 plus 3000 divided by 400. Sorry, area is what? 200. For the second material, area is what? 200. This is our first material. And Young's modulus will be 210. For the steel, we have 210. 210 into 1000. When you do that, you can get R in Newton. Try to calculate and tell me the answer. This is called principle of superposition. Principle of superposition. Eleven into 10 power minus 6 into 2000 into 10 plus 12 into 10 power minus 6 into 10 into 3000. 0.58. 0.58, that is equal to R. 2000 divided by 400 divided by 70 divided by 1000 plus 3000 divided by 200 divided by 210 divided by 1000. We are getting 1 upon 7000. So from here R will be what? 7000 into 0.58. 4060 Newton. That is the reaction force, and that will be same. That will be same. In the same problem, they would have asked what is the thermal stress in aluminum. What is the thermal stress in aluminum? R divided by area of aluminum. What is the thermal stress in steel? R divided by area of steel. But the nature will be what? Compressive. But the nature will be what? Compressive. Make a note of it. Now here, my dear friend, as we have noted down these things, further we will try to explore. Again, the next question. The next question I am just putting in front of you. You try to solve and let me know the answer. Because same problem we have discussed in our previous session of torsional loading. You try to answer. It's pretty straightforward. The two bars which are connected in series, once again here. So let me take this particular question in the next page. The twisting moment T is applied at the free ends, having a length of 2L, having a length of L. The angle of twist theta at the free end would be what? Let's take A, B, C. They are asking theta C. I told you theta C will be theta C with respect to A. Always remember angle of twist are calculated of any point with respect to fixed end. Theta C with respect to B plus B with respect to A. How to determine theta C with respect to B? That is theta VC, PVC, LBC, GBC, JBC. All I want to say, theta is what? TL divided by GJ. Right? TBC. Now, when you calculate twisting in both the segment, when you calculate twisting in both the segment AB and BC, you will find twisting in AB is what? T. That is minus T or plus T? Minus T. According to our sign convention, what we are taking here, we are taking when you convert into this loading into line diagram, you will find A, B, let's say C. You will find your forefinger you try to rotate in the same sense of twisting movement. Your thumb will be going towards the left directions. Your thumb will be going towards the left directions. And here you have the reaction torque at A. That is equal to T. That is obviously equal to T. So in both the sections, we have T, AB will be minus T, TBC will be minus T. Why minus B? Why minus T? Because according to our standard sign conventions, right? According to our standard sign conventions, what we have followed in our classes, that whenever at any section we have twisting movement like this, then Txx will be minus T. Whereas we have any section when the twisting movement is like this, then Txx will be plus T. Plus T. TBC is what? T minus T. LBC is what? 2L. Sorry, LBC is what? L only. LBC, length of BC section. The length of BC section is what? L only. GBC is what? Both are made up of same material? Yes. Pi d power 4 by 32. What about theta B with respect to A? Theta AB, TAB, LAB, GAB, JAB. TAB is what? Minus T into 2L divided by what? G pi 2 to the power 4 divided by 32. Right? So here when you just write 64 TL divided by pi G 16 d power 4 minus 4 TL divided by pi G d power 4, and here you will be getting 32 minus TL pi G d power 4. So when you add this together, you will find minus 36 TL divided by pi G d power 4, because 32 4, when you combine this value and this value, you will find my different 36 TL divided by pi G d power 4. Now if you want to find the magnitude only, so 36 will be the answer. 36 TL divided by pi G d power 4. C will be correct. This is one of the important thing. Now try to answer this 65 question. 65th question, what they are saying, in most brittle material, the ultimate, I told you in our last class also, when we have been discussing the Rankine's theory, right? I told you it is an unsymmetrical section, right? Ultimate strength in compression is larger than ultimate strength in tensile. For what? For brittle material. Brittle materials are very, very weak in tension, very, very weak in tension, right? But very, very strong in compression. Why? Because presence of flaws and the cracks. Generally, any material, they are not a defect free. They are definitely having some defect. They are definitely having some crack. Any material you will take, they will be having certain cracks. Generally, when you keep on applying the tensile load, this crack will be propagating and they will be more widen and widen during its functionality time. But generally, when you apply compressive load, these cracks, whatever the cracks and flaws are there, they will try to fill. They will be getting shorter and shorter, right? That much of highlightment of cracks will not be appear when you just apply compressive load. So that's why compression strengths are very, very high in most of the brittle material than the ultimate tensile strength. But this is not a case in case of what we talk about ductile materials, right? In ductile materials, there will be local yielding. Because of the local yielding, there will be plastic deformation will be happening, and because of that, they will try to adjust the plastic failures. So all I want to say, for a brittle material, I'm not talking about ductile materials. There is a separate talk on the ductile material, but as far as the brittle material is being concerned, they are having the ultimate compressive strength larger than ultimate tensile strength. Right? Even I have talked about the same thing in Rankine's theory in our previous session of ISRO. That why we have unsymmetrical when we plot sigma 2 and sigma 1, right? That's why each and every discussions are very, very important. You have to discuss surrounding things. Not only we have to just be robot in solving the previous question. Again, I'm telling you, literally it will not help even a 1% also when you just by hearting the previous year questions. You have to see what are the other scenarios and why they have framed the questions. What are all the options? What is the meaning of C option? What is the meaning of D option? What is the meaning of A option? Until unless you're not bothering about other options which are wrong, you are not at all able to crack exam. So here you have ultimate tensile, but ultimate compression here, ultimate tensile, ultimate compression here, and that's how you get unsymmetrical square section. That's what we have seen in the Rankine theory for a brittle material, which are very much suited that theories of failure for brittle materials, right? Now, again, try to see the for the spring system shown in the figure, what is the equivalent stiffness will be. Now, it's a very easy question. It's straightforward. Try to solve it. Very, very easy and very straightforward. A rigid bar is there. As you can see, the rigid bar. What will be there? See, this spring and this spring. Spring number one, spring number two, spring number three. Spring number one and two, they are connected in what? Parallel combination. What is the equivalent stiffness? What will be the equivalent stiffness, my different 2K? Here it is 2K. Now we are applying any amount of load, let's say. Now this 2K and 2K, because see, when the bars in parallel, or let's say the spring in parallel combinations, spring in parallel, like this. If it is K and K, then what is the K equivalent? K equivalent will be K1 plus K2, which is K plus K. When the bars in series combination, as you can see, these are in what? Series combinations. Right. Then what will happen? What is the K equivalent? K equivalent will be 1 upon K1 plus 1 upon K2. Here K1 is what? 2K plus 1 upon 2K. So 1 upon K equivalent will be what? 2 into 1 upon 2K. So K equivalent will be. It's a very simple. It's a very, very simple. For bar, how we are getting this thing? Generally, for the parallel combination, we say deflections in both the springs will be same. Then equivalent deflections. And then we say here deflection will be can be written as here. It can be written as W, the loads which we have applied. For example, the loads gonna be shared in both the springs. Let's say W will be W1 plus W2. Here we can write here W1 divided by K1, W2 divided by K2. Right. So here W that is equal to W1 plus W2. So what we can write? Here let me take springs in parallel. Note down. I am explaining you how we are getting one K equivalent will be K1 plus K2. Please make a note of it. Suppose we have springs, they are connected in parallel. Spring number one, spring number two. Now we are converting in equivalent stiffness K equivalent by applying the load W. We know that deflections in bar one and bar two will be same. And W is what? W1 plus W2. W, what is the W load? K equivalent into delta. K equivalent into delta. What is the W1? K1 into delta 1. What is the W2? K2 into delta 2. K is what? Is stiffness. Delta is same everywhere. So what is the K equivalent? K1 plus K2. Similarly, when the bars in series combination, you know that when springs in series combination, deflection, you know the deflection is equal to what? Deflection 1 plus deflection 2 when they are connected in series. Deflection will be unequal, but whatever the load which we have applied, what we can write, my different, the loads will be what? the loads will be same. Whatever the load is there, this W, this load will be in both the spring will be same. W1 equal to what? W2. In the same way, when you do that, W is what? Delta is, you can write what? W divided by K equivalent. That is W divided by K1 plus W divided by K2. So this W will cancel out. You will get here K equivalent as 1 upon K1 plus 1 upon K2. 1 upon K1 plus 1 upon K2, my dear friend. 1 upon K1 plus 1 upon K2. That's how we will be getting the solution for this question. Now try to see this particular question. First of all, read that. Do not directly jump onto the conclusion point. First, see very carefully with your open eyes and try to answer it. A round uniformly tapered bar, right, of a length L, having a Young's modulus E, has a diameter D. One end there is a diameter D, other end there is a diameter of 2D. The bar is pulled with the axial force F. What is the extension produced? How much of deformation will be there? Axial deformation they are asking. Again, very straightforward question. What we have seen in our strength of material also, we have seen this similar question. So whenever we take prismatic bar subjected to the load P, we know deformation is PL divided by AE. Now we cannot directly use this formula because here area is not same everywhere. Area is what changing, right? Area is what changing. So accordingly we have to proceed. So very first of all, note down, then we will discuss. Okay, so all of you have noted down. So now note down the figure. Here, elongation of a tapered bar. Note down. Let's say this is a fixed end, diameter D, diameter 2D, and here we are applying the load P. Having a length L. At any section, I'm considering section XX from here. Let's say it is X, and the diameter is here what? DXX, for example. What about the area at XX? Pi by 4, pi by 4 DXX square. Now, what is the DXX? That's a very simple. D1 minus D2 is changing over the length of L. Then dxx minus d2 will change over the length of x. So here dxx will be what? d1 minus d2 into x by L plus d2. Here k I am writing as d1 minus d2 by L. So here dxx can be written as kx plus d2. So pi by 4 kx plus d2 whole square. Whole square. Now what you have to do, you simply perform integration 0 to L. What is the load? P. What is the length I'm considering? Dx. I'm taking one small elementary strip, right? P into dx. Area is what? Pi by 4 dxx square, that is kx plus d2 whole square into e into e into e. Now you simply do integrations. That's a very simple. So 4p divided by pi e. Now integration of here integration of 1 upon kx plus d2 whole square into dx. How much of integration by different? That's again a very simple task, right? But dx, what is the integration dx divided by x to the power n minus n plus 1 minus n plus 1, right? The same thing we are putting here, kx plus d2 minus 1 divided by minus 1, 0 to L. into 1 upon k, because whatever the differentiation is there, the coefficient of this differentiation, we have to keep it in denominator. I hope you know integration, right? All I want to say. So delta will be minus 4p divided by pi e into k, 1 upon d1 minus 1 upon d2. So delta can be written as 4pl divided by pi e d1 d2, d1 d2. This will be the final formula. This will be the final formula. Here k I have replaced with d1 minus d2 by l, and I have simplified. There's a one more step, but I have directly noted down this step. So what is the formula you're getting? Delta 4pl divided by pi d1 d2 into e. Put that value. Load is what? F 4fl divided by d is what? D1 is what? D1 is d. It is 2d into e. So final formula is what? 2fl divided by pi d square into e. A will be correct. Even you can simplify, even you can understand whether you are going in the right direction or not. Simply putting d1 equal to dt for a uniform section diameter d. Whether you're getting the same answer, you can verify. Note down. I hope you can do from here to here this step. That's a very school mathematics. Upper limit minus lower limit. Remember k, d1 minus d2 by l. Accordingly proceed. Note on the next question. First of all, try to see, observe very carefully, read the problem, try to make a habit of read the question. All means all the lines of the question has to be clearly, basically what reading should be clear. A solid shaft can resist the bending moment. That means a solid shaft is being subjected to bending moment also and twisting moment also. Having a bending moment said that 6 kilonewton meter, and twisting moment it has been said of 8 kilonewton meter. Together, the maximum torque that a shaft can resist when applied alone. That means they are asking what is the equivalent torque. Whenever both bending moment twisting moment is acting, what is the maximum shear stress? We know the formula half of sigma x square plus tau plus 4 times of tau xy square. How are we getting this formula? Sigma 1 minus sigma 2 by 2. That's we know that. This is the formula we have. When the circular shaft is subjected to the bending moment, what is the formula for the bending stress? 32 m divided by pi dq. And when it is subjected to twisting moment, then we know 16t divided by pi dq. 16t divided by pi dq. Right? Now further what we can write? Tau maximum as half of under root of 32 m divided by pi dq whole square plus 32t divided by pi dq whole square. Further, what we can write? Tau max. Tau max I can write 32 divided by 2 pi dq under root of t square plus m square, right? Now this tau max, we know that 16t equivalent divided by pi dq. That is the equivalent torque, we have to calculate. When we just apply twisting moment alone, T equivalent. And this tau maximum is what? 16 divided by pi dq under root of t square plus m square. So this and this will cancel out. So what is the T equivalent? T square plus m square. Now, what is T square? 8 square, m square, c 6 square. Now when you calculate, you will be getting what? 10 kilonewton meter. Make a note of it. C will be correct. C will be correct. Sometimes they ask equivalent bending moment also. Sometimes they ask equivalent bending moment also. Sometimes with the same problem, they would have asked equivalent bending moment. Equivalent bending moment. If the bending moment would have been applied alone, then what is the equivalent? Then what is the equivalent bending moment? What is the equivalent bending moment? That's again a very simple task to do that. What is the sigma 1? That is sigma maximum. Sigma x by 2 plus sigma x by 2 whole square plus tau xy square. Sigma x, I told you. What is that? 32 m. Note down this also. We have got the answer happily, but I told you, do not just depending on the previous year questions. You have to solve other things also regarding that particular questions. So what will be the equivalent bending moment? That's what we are calculating. See, you have to certain thing, you have to remember that you have to at least revise 5 times each and every subject before ISRO paper, so that in examination all you should not think whether this is a formula, that is a formula, those are the formulas. If you start doing like this in examination, all gone, right? Sigma max will be what? 32 m divided by pi dq into 2 plus 32 m divided by pi dq into 2 whole square plus 16t divided by pi dq whole square. So my different here, what you are understanding that, what you are understanding from here, you are getting here 16 divided by pi dq. Here I am writing m plus under root of m square plus t square. This is the sigma max. And we know that sigma max is what? 32 m equivalent divided by pi d cube. If bending moment would have been applied alone, m equivalent. So this will be cancelled out. So what is the m equivalent? Half of m plus under root of m square plus t square. So this is the m equivalent based on the maximum principal stress theory, right? Maximum normal stress theory. So half of m is what? 6 plus 10. So what is this? 16 divided by 2, that is equal to 8 kilonewton meter. That would have been the answer. If they would have been asking m equivalent. M equivalent. Right? Make a note of it. So according to maximum normal stress theory or Rankines theory, this is the m equivalent. And according to von Mises, if I would have been asking you what is the equivalent moment, right? Note on the one more question. What is equivalent bending moment based on von Mises? I'm telling you the answer, but you can verify as a homework whether you are getting this thing or not. M square plus 3 by 4 t square. That will be the M equivalent based on von Mises. So three questions I have discussed regarding the same one question. Right? Note down this 71 question. The two shafts of the same length and the material are connected in series. Connected in series. Let's say the diameter is d1, diameter is d2, and d1 and d2 is 2. Then they are asking what is the ratio of their angle of twist. Twisting moment is same, length is same, g is same. Then what is the angle of twist? Theta 1 by theta 2. T is same, L is same, G is same. Only J will be different. So we can write J2 divided by J1, theta 1 divided by theta 2. Theta 1 divided by theta 2 will be d2 power 4 divided by d1 power 4. 1 upon 2 to the power 4, that is 1 upon 16. So that is theta 1 divided by theta 2 will be 1 upon 16. So what about their ratios? Either you can write theta 2 divided by theta 1, that is 16. This will be correct. What is the polar moment of inertia? Y d power 4 divided by 32. Two shafts which are connected in series. If they would have been asking the two shafts which are connected in parallel combinations, then the ratio of angle of twist will be what? Same, 1. Moving on to the next question. A concentrated load F acts on a simply supported beam of a span of length L at a distance of L by 3 from the left support. The bending moment at the same location, the bending moment at this location, at the location C, the bending moment at this particular location would be what? The bending moment at this location C will be what? Bending moment, we know that at the ends will be 0, and at here at the C point it will be maximum. A, C, B. What is the bending moment at C? See the reaction force RA and RB. How to calculate RA and RB? Ra plus Rb, that is equal to F. Now you can take summation of moment about B point to be 0. Then Ra into L, that is equal to F into 2L by 3. So Ra will be what? 2F by 3. So this is 2F by 3. So 2F by 3 into L by 3. So 2FL by 9. 2FL by 9. That will be correct. C will be correct. Note down. Note on the next question. The next particular question they have asked basically from first chapter, that is the elongation of what? Elongation of a bar due to its own weight. Elongation of a bar due to its own weight. So here own weight, what will be there? There is a no load, but because of the own weight, it will be basically what? Uh, Subjected to some kind of deformations, right? And now we have to calculate that deformations. Elongation of a prismatic bar due to its self weight. Elongation of a solid bar due to its own weight. Now, at any section when you consider any section, there will be certain weight because of this, right? It is just like some materials are there, some person is there who is basically what, applying some kind of load, right? You see, it is basically what, pulling it downward. Because of that, there will be deflections. What is the load at xx? What is the load at xx? Because of let's say this is x, cross sectional area is a, then what is our total load? Mg. Then what we can write? Rho g into a into what? X. That is the volume. A into x is what? Volume. Rho g is what? Gamma into a into x. That is the load which are acting at xx, right? And that load is what? Varying linearly. Once we got the axial load, once we got, my dear friend, axial load, what is the next segment? What is the next segment? Once we got the load, what is the next segment we have to follow? We have to follow here. Once we got the load, now deflection. Deflection is what? 0 to L Wxx into dx divided by A into E. 0 to L gamma into A into x into dx divided by A into E. This will cancel out. So what we'll be getting? Gamma into E x square divided by 2, that is 0 to L. So what is the deflection in the prismatic bar due to its self weight? That will be gamma into L square divided by 2E. Now look at the option. Total elongation is what? Gamma into L square divided by 2E. Gamma is what? I told you rho g, right? So rho g into L square divided by 2E, right? Rho g into L square divided by 2E, so B option is correct. That is the total elongation in prismatic bar. Make a note of it. B will be correct, right? Note down elongation of a conical bar also. Elongation of a conical bar also. Note down elongation of a conical bar due to its own weight, due to its self weight. Conical bar, which is placed like this. At any section, you can calculate the load. Because of this, there will be some elongation. And here it is there at a distance L. The total length is what? L. Here also, the total length you can consider this has to be L. Now here, what is the load which has been acting here? What is the load which has been acting? So you can consider a small strip of a length dx and having a diameter dxx. So here the load is also varying as well as diameter is also changing. So while performing integration, you have to write wxx into dx divided by axx into e, 0 to L. But what is the value of diameter at a section dxx? So here we have the diameter d, for example. Then of course dxx will be what? Dxx will be d into x by L because it is varying linearly. That is the one thing we got to know. What about the next segment? What is the load which has been acting? What is the load which has been acting? The load which has been acting, wxx will be here, that is a gamma axx into x divided by 3. Because see, that will be the volume of this particular segment. This particular segment, what is the volume? 1 by 3. 1 by 3 area, 1 by 3 of volume. 1 by 3 of volume. Volume is what? See, gamma once again is what? Mg. Weight is what? Mg, but by 3 here. The weight of this cone will be mg by 3, not like a prismatic bar. Mg is what? Mg is what? Gamma. Here mass is what? Volume into density. Density into g will be what? Density into g will be rho g. Density into g will be rho g. So here what we can write? That is rho into volume divided by 3. Volume is what? Area into x. Area into x, right? So we can write here further, area xx will be pi by 4 dxx square. Put all those things together into that integration 0 to L, and you just do integrations. What you will be getting? What you will be getting? Wxx. Wxx will be gamma into axx into x into dx divided by 3 into axx into E. This will cancel out. So what I will be getting? Gamma divided by 3E, x square divided by 2 from 0 to L. So what you are getting total deformations? Gamma into L square divided by 6E. Make a note of it. Very, very important. Elongation of a conical bar. Elongation of a conical bar. No. Moving on to the next question. Probably this. Okay. This will be the second last question. The ideal critical buckling load for a column fixed at both the ends. I told you in our last class, if it is fixed at both the ends, what is the alpha? 1 upon 2. Right? So what is the P critical load? What is the P critical load? Tell me guys. Pi square EI minimum divided by alpha square L square. So P critical will be pi square EI divided by L. Alpha is what? 1 upon 2, 1 upon 2 whole square 4, 4 divided by L square. So C will be correct. Here remember actual formula is what? N times of we used to write. Here N is what? 1. Fundamental mode of buckling we are taking. Here we are taking fundamental mode of buckling. Fundamental mode of buckling. N equal to 1. Fundamental mode of buckling. If this would happen, that means buckling will happen like this. Actual figure if I draw, then the buckling will happen like this. If at all buckling would have been occur like this, for example, that is n equal to 2. That is a fundamental. That is the second fundamental mode of bucklings. In that case, then the formula would not be different. The formula would be different as what we are seeing here. So this is corresponding to fundamental mode of buckling. It is corresponding to fundamental mode of buckling. Make a note of it. Here you can add n square. Exact formula. If somebody will be asking you, this is the exact formula: n square into pi square EI minimum divided by alpha square L square, where n is what? Number of modes in which the buckling is taking place. Right? N equal to 1. This is corresponding to n equal to 1. This is corresponding to n equal to 2. Right? So this is fixed at both the ends. So 4 pi is pi square into EI divided by L square. That will be the buckling formulas. Now, not on the last problem, and this is very important. They are asking what are the von Mises equivalent stress, right? So we have different formulas in von Mises theory. I will be writing all the formulas for you so that equivalent stress when the material is subjected to, see whatever the material they have given, this 3D state of stress they have given, where it is being subjected to principal stresses. One is 300 megapascal, one is 100 megapascal, other will be 150 megapascal. Sigma 1 is what? 300 megapascal. Sigma 2 is what? 150 megapascal. Sigma 3 will be minus 100 megapascal. Because there is a no shear stress, so all the planes will be principal planes. All the planes will be principal planes. So here sigma equivalent, that we used to write sigma yt divided by n is what? Factor of safety. We have the formula, note down, half of sigma 1 minus sigma 2 whole square, sigma 2 minus sigma 3 whole square, whole square. This is the formula we have, whole bracket. Then what is the sigma equivalent, my friend? Sigma equivalent will be what? Sigma 1 minus sigma 2, 300 minus 150 whole square, 150 plus 100 whole square, 100 minus 300 whole square, means minus 100 plus 300, because, sorry, what I'm writing here, sigma 3 is minus 100, and that will be minus. Right. So that will be formula. So when you calculate correspondingly the values, how much of value you will be getting? Plus 250 square. When you calculate, you will be getting 350 megapascal. This is what we got the answer, that is 350 megapascal. But note down the other formulas also, which I'm telling you right now. Sigma equivalent in terms of sigma xx, sigma yy, sigma zz. Note down in terms of that. We have very big formula, half of sigma x minus sigma y whole square, whole square plus plus 6 whole square, whole bracket, whole bracket, like this. If they would have been given in sigma x, sigma y, sigma z, tau x y, tau y z, tau z x, in terms of that, you can remember like this. Very, very important. Half is a whole common, right? Please note down very carefully. So I hope you understand, you know, you understood what actually we have been talking about in this session. And, you know, so the last session will be ISRO 2020. That year we have the questions again from the strength of material and machine design, that we will take, you know, in upcoming basically session of ISRO, right? So thank you all.